Hello guys, and welcome to this video. My name is Manuel Joseph Loquias, and I have been assigned to do a lecture video on the topic of surface integrals of scalar fields. This lecture video consists of two parts, and this is the first of them. Okay, here we go. Suppose we have a lamina in the shape of region R that is not necessarily homogeneous. That is, the density varies among the points of the lamina and is given by the density function f of xy. Recall from the lecture on applications of double integrals that the mass m of the lamina is given by the double integral of f of xy dA over the region R. In this lecture, we consider laminas that are not planar but curved. That is, the lamina is in the shape of a smooth surface S in three-dimensional space with density function f of xyz. Our goal is to find the mass of the lamina S. To obtain the mass of lamina S, we employ the basic ideas in formulating an integral, which are usually summarized into three steps: partition, approximate, and sum. For the partition part, we divide the lamina S into small patches, as shown here in the figure. We assume that there are n patches, labeled S1 up to Sn, with respective surface areas delta sigma 1 up to delta sigma n. We focus on an arbitrary patch, which we refer to as Si, shown in red in the figure, with area delta sigma I. Afterwards, we choose any point Pi star with coordinate xi star, yi star, zi star on each patch Si. We now move on to the approximate part. For this, we assume that the patch Si is so small that it is almost homogeneous. That is, the density at every point of Si is roughly the density at Pi star, which is f of Pi star. Since we now assume that the patch Si has constant density f of Pi star, the mass of the patch Si is approximately equal to the density f of Pi star multiplied with the surface area delta sigma I of Si. Hence, we now have approximated the mass of each of the n patches of S. For the sum part, we get the sum of these n approximations to obtain an estimate of the mass of the entire lamina S. From our discussion, we then define the mass m of lamina S to be the limit of the summation of f of Pi star multiplied with delta sigma I, where the sum runs from 1 to n, and the limit is taken as n approaches infinity. Recall that the sum here was our approximation of the mass of the lamina S. In order to make this approximation as close to the actual value of the mass m of the lamina S, we make the number n of patches sufficiently large and also make the maximum dimension of each patch sufficiently small, so that the patch Si is indeed almost homogeneous. That is what the limit as n approaches infinity here actually means. This leads us to the definition of the surface integral of a scalar field. Let f of xyz be a function that is continuous on a smooth surface S in three-dimensional space. We define the surface integral of f over S to be the limit of the summation of f of Pi star times delta sigma I, where the sum runs from 1 to n, and the limit is taken as n approaches infinity, provided that this limit exists. We use the following notation. We have a double integral with subscript surface S. We have the integrand f of xyz, And we have d sigma, where sigma represents surface area. Clearly, the next question is how do we evaluate this surface integral without going through this limit definition? Recall that the line integral of a scalar field along curve C is computed by writing it as a definite integral with respect to the parameter t of some parametrization of curve C. Analogously, we will write this surface integral over the surface S as a double integral over the parameter uv of some parametrization of surface S. To that end, recall from the lecture on applications of double integrals that if a smooth surface S has parametrization R of uv, where uv is in some closed and bounded region D in the uv plane, then the surface area delta sigma I of the ith patch is approximated by the magnitude of RUUIVI cross RVUIVI multiplied by delta U delta V. From that, it follows that the surface area of f of xyz d sigma over the surface S is equal to the double integral of f of R of uv times the magnitude of RUUV cross RVUV dA over the region D. Notice that d sigma becomes the magnitude of RUUV cross RVUV dA. Furthermore, since this double integral will be written as an iterated integral in terms of the parameters u and v, then we need to express f of xyz in terms of the parameters u and v. We illustrate this in the next example. Suppose you are being asked to evaluate the surface integral of x squared plus y squared d sigma over the surface S, where S is defined by R of uv equals u, v, u minus v, and where u and v satisfy u squared plus v squared is less than or equal to 4. Remember that to evaluate this surface integral, all we need to do is to write it as a double integral over some region in the UV plane. For that, we have the double integral of, first we need to express x squared plus y squared in terms of the parameters u and v of surface S. Since x is equal to u and y equals v, we have x squared plus y squared to be u squared plus v squared. Recall that d sigma becomes the magnitude of Ru cross Rv dA over some region D. Before we can continue, we need to identify the magnitude of Ru cross Rv and the region D in the UV plane. We start with the magnitude of Ru cross Rv. For that, we need the vector Ru cross Rv. Note that the vector Ru has components 1, 0, and 1, which are the derivatives of u, v, and u minus v, respectively. Similarly, Rv has components 0, 1, and minus 1. This means that Ru cross Rv has components 0, minus 1, which is minus 1, 0, minus negative 1, which is 1, and 1 minus 0, which is 1. Continuing now with the original problem, I obtain the double integral over the region D of u squared plus v squared multiplied by the magnitude of Ru cross Rv, which is just now the square root of the sum of the squares of the components of Ru cross Rv. which is just 1 plus 1 plus 1 dA. Before we continue further, let us identify the region D. Note that region D is a set of points in the UV plane that satisfy the inequality u squared plus v squared is less than or equal to 4. The graph of the equation u squared plus v squared equals 4 is the circle in the UV plane with center at the origin and radius 2. Note that all the points on the circle satisfies u squared plus v squared equals 4, while this point, for instance 1, 0, inside the circle, satisfies u squared plus v squared is less than 4. Indeed, 1 squared plus 0 squared is equal to 1 is less than 4. This implies that region D is exactly the circle and its interior. We are now ready to finish solving the original problem. We need to write this double integral as an iterated integral. First, we factor out this constant from the double integral. We get square root of 3. Note that the region D in the UV plane is a circle, and so it will be convenient to use polar coordinates in our integration. Continuing, we obtain the integral of the integral u squared plus v squared in polar coordinates is r squared. dA in polar coordinates is r dr d theta. Observe that the values of r vary from 0 to 2. Hence, the limits of the inner integral are 0 and 2. Also, the values of theta vary from 0 to 2 pi. Hence, the limits of the outer integral are 0 and 2 pi. All that remains is to evaluate this iterated integral. We have the square root of 3 times the integral from 0 to 2 pi. The integral of r cubed is r to the 4th all over 4, evaluated from r equals 0 to r equals 2 d theta. Here, we obtain 2 to the 4th over 4, or 4, minus 0, which simplifies to 4, and we can factor it out from the single integral. I get 4 square root of 3 times the integral from 0 to 2 pi of d theta. Since the integral of d theta from 0 to 2 pi is just 2 pi, we obtain the final answer of 8 pi square root of 3. For the next example, you are being asked to find the mass of this donut-shaped surface, also called a torus, with parameterization r of uv equals the quantity 2 plus cosine u times cosine vi hat plus the quantity 2 plus cosine u times sine vj hat plus sine uk hat, where the values of u and v are between 0 and 2 pi, if a density at any point x, y, z in the torus is given by the function f of x, y, z equals x squared plus y squared plus z squared. Recall from the start of the lecture that the mass m of the torus is given by the surface integral of the density function f of x, y, z d sigma over the torus. Next, we write this surface integral as a double integral over some region in the UV plane. We obtain the double integral of, we need to express x, y, z in terms of UV, which we write as f of r of UV multiplied by d sigma, which is just the magnitude of ru cross rv dA over some region D on the UV plane. We need to compute for the magnitude of RU cross RV, f of RUV, and identify the region D in the UV plane. We start with f of RUV. For this, we need to substitute the value of x, y, and z of r of uv in your function f of x, y, z. Thus, we obtain x squared to be the square of 2 plus cosine of u multiplied by cosine squared of v plus y squared to be the square of 2 plus cosine u multiplied by sine squared v and z squared to be sine squared of u. We can factor out the square of 2 plus cosine u from the first two terms, which when simplified becomes 4 plus 4 cosine u plus cosine squared u multiplied with what is left, which is cosine squared v plus sine squared v, which reduces to 1. And plus the remaining term, sine squared u. Note that cosine squared u plus sine squared u also simplifies to 1, and so we end up with f of RUV, which is now 5 plus 4 cosine of u. We write this result here in the line below. We now compute for the magnitude of RU cross RV. For this, we need to find RU, RV, and RU cross RV. To obtain the components of RU, we need to find the partial derivative of each component of R of uv with respect to u. Hence, RU has x component, negative sine u cosine v, has y component, negative sine u sine v, and has z component, cosine of u. Similarly, RV has x component, 2 plus cosine of u, multiplied by the negative of sine v, has y component, 2 plus cosine of u, multiplied by cosine of v, and has z component, 0. We proceed to find the cross product of RU and RV. RU cross RV has x component, the negative of 2 plus cosine u, multiplied by cosine u cosine v, has y component, the negative of 2 plus cosine u, multiplied by cosine u sine v, and has z component, the negative of 2 plus cosine u, multiplied by sine u cosine squared v, minus the quantity 2 plus cosine u, multiplied by sine u sine squared v. Observe that we can factor out the negative of 2 plus cosine u from each component of RU cross RV. Doing that yields the negative of 2 plus cosine of u multiplied by the vector with x component, cosine u cosine v, with y component, cosine u sine v, and with z component, sine of u. This is because we can still factor out sine u in the third component here, leaving cosine squared v plus sine squared v, which reduces to 1. We need more space to proceed, so we copy RU cross RV on this side and continue. We can now compute for the magnitude of RU cross RV. Observe that negative of 2 plus cosine u is a scalar factor of RU cross RV. Hence, for the magnitude, we have a factor of the absolute value of negative of 2 plus cosine u multiplied by the magnitude of this vector, which is given by the square root of cosine squared u cosine squared v plus cosine squared u sine squared v plus sine squared u. Simplifying, note that 2 plus cosine u is always positive. Hence, the absolute value of the negative of 2 plus cosine u is just 2 plus cosine of u. Furthermore, note that cosine squared of u can be factored from the first two terms, which leaves cosine squared v plus sine squared v that reduces to 1. Hence, we are left with cosine squared u plus sine squared u, which is just 1, and we end up with the square root of 1, or 1. Therefore, the magnitude of Ru cross Rv is 2 plus cosine of u. We write this result in our integral here. We now identify region D in the UV plane. Recall that the parameters u and v satisfy this inequality. Since u is between 0 and 2 pi, then region D should lie between the vertical lines u equals 0 and u equals 2 pi. Also, since v is between 0 and 2 pi, then region D should lie between the horizontal lines v equals 0 and v equals 2 pi. Therefore, region D is a square in the first quadrant with vertex at the origin and side length 2 pi. Finally, we are ready to compute for the mass m of the torus. To that end, we write this double integral as an iterated integral. We obtain the integral of the integral of, simplifying the integrand, we have 10 plus 13 cosine of u plus 4 cosine squared of u. If we choose to integrate first with respect to the parameter u, then we have du dv, and we find that the limits of the inner integral and the outer integral are both 0 and 2 pi. All that remains is to evaluate this iterated integral. In order to integrate with respect to the parameter u, we need to remember that 2 cosine squared u can be written as 1 plus cosine of 2u. Hence, we now have the integral from 0 to 2 pi of the integral of 10 plus 2, which is 12 with respect to u, is 12u, plus the integral of 13 cosine u with respect to u is 13 sine u, and the integral of 2 cosine 2u with respect to u is sine 2u, evaluated from u equals 0 to u equals 2 pi dv. Note that sine u and sine 2u, when evaluated at u equals 0 and u equals 2 pi, are both 0. And hence, we are left with this constant, 24 pi, which we can bring out of your integral. So I have 24 pi multiplied by the integral from 0 to 2 pi of dv. And since the integral from 0 to 2 pi of dv is equal to 2 pi, I end up with the mass of the torus to be 48 pi squared. We end this video with the following remark. If the function f of xyz is the constant function 1, then the surface integral of f of xyz d sigma over the surface S, or simply the surface integral of d sigma over S, gives a surface area of S. In fact, if S is parameterized by R of uv, where uv is in the region D, then the surface integral of d sigma over s becomes a double integral of the magnitude of RUUV cross RVUV dA over the region D, which is exactly the result that we obtained in the lecture on applications of double integrals. Furthermore, this remark is analogous to the previous result that the line integral of ds along a curve C is the arc length of C. In the next part of this video lecture, we will talk about surface integrals where the surface is defined as a function in x and y. That's it, and I hope to see you in the next video.